So in this video we're going to talk about RC circuits. And before we go into anything, why is it called an RC circuit? Well, to be quite frank, right now in my circuit what I've drawn is I have a switch. I've got a capacitor which has a positive charge on the top, I've got a negative charge on the bottom, and I have a resistor. Any RC circuit is a circuit that has a resistor and a capacitor. So, where I want to go with this is we want to talk about discharging right now. I've got a charged capacitor, and as I close this switch, what's going to happen with our charged plates? Because right now, these two charges would like to meet up, opposites attract, so they would like to go through the plate. But our dielectric insulator won't allow that to happen. But if I close the switch and I close my circuit, what I allow to happen is the flow of the electrons. And we know, based off of the circuits that we used earlier with just resistors, the flow of electrons is also what? Well, the flow of electrons is the current, right? If I have current flowing through, that's like the number of particles or the number of electrons that are moving. So, and we also know that at any point, the flow of the electrons in a closed loop has to be the same, right? I can't have 10 electrons here flowing through per second and 8 electrons here flowing through per second. It just doesn't make sense because they only have one path that they can take. So that also means that the flow of the electrons through the resistor, or the current through the resistor, and what we can say the current of our capacitor are going to be the same, or IR plus IC equals 0. Now what I have drawn is I have equivalences for these. And when we looked at Ohm's law, we knew that current was the same as the voltage over the resistance. And we know that the amount of electrons on a capacitor, if I change the number of electrons, the change of charge over the amount of time it takes would tell me the flow or the current of a capacitor. So, as I have a whole bunch of electrons here and they leave, the rate at which they leave, flow of electrons per second, or the change of charge per second, will give me what the current is. Just like I explained in our last video, we don't really like to use charge a whole lot. It's a harder value to calculate. So what we're going to do is we're going to substitute our charge of a capacitor into our formula, where we knew that the equivalence was capacitance multiplied by the change in voltage. Right? The difference in potential between my top plate and my bottom plate, which is going to be my change in voltage over the change in time. Right? What I also did was I removed the 0, I made these two equivalent, which turned this into a negative voltage. Negative voltage over R is equal to capacitance multiplied by change in voltage over the change in time. I'm going to get this all by itself, the change in voltage over time, so I'm going to have to divide by C on both sides. And then I'm going to go through I'm going to skip a few steps, and I'm going to write down what our final value should be, our final formula should be, once we do some simplification. So what I ended up doing was I ended up taking my capacitance, I divided it over to the other side, so I got voltage over RC is equal to change in voltage over the change in time, and then I ended up getting both of my voltages over to one side, where I had the change in voltage over voltage of the resistor, I'll just put VR, and VC, and I multiplied by T on both sides. So I ended up having change in time over RC is equal to my change in voltage of a capacitor over my voltage. Then from there I had to do some other calculations in order to get my final value. And what I did was I said my voltage as a function of time. So as time progresses, my voltage changes. And how it changes is based off of my original voltage, or the change in potential between my top plate and my bottom plate, and it's multiplied by the exponential function of my negative t, right, the negative amount of time that passes over RC. Now, this RC, resistance multiplied by the capacitor, by the capacitance, is equal to tau, right? We might see negative time over RC, but we can also see it as negative time over tau, which is our time constant. So if I just take my resistor value and I multiply it by the capacitance that I have, that is my value of tau. What we're going to look at how my voltage changes over the amount of time. Mr. G, can you please explain to me what you mean by a change in voltage? That concept right now is, what do you mean by the change in voltage? Because voltage is kind of like the change in my potential. So can you give me a way to better understand it? I can. And the way that I want to do it is I want to do it thinking about the capacitor as a water bottle full of water, right? And what happens right now is I have a buildup of charge on each plate, and those charges want to come together. As soon as I close the switch, they're allowed to. And how fast they do it, how quickly they want to move, or how much push there is for them to come together is based off the amount of charge that there's built up on the plates, right? And that's what I'm going to do with this, is there's a buildup of energy. There's a lot of push for all the water molecules that are in here to want to leave. And there's a hole that I cut in the bottom, right? And so as time progresses, which is why it's written as an exponential function, as time progresses, how much push is there to go out? And as time goes on, my value of charge on both of these decreases, or the amount of push decreases. And we can think of that, if I were to once I take my finger off the hole in the bottom here, how much push is there, how far away this water goes, as time progresses, is going to decrease, right? If we look at how this falls, we can see it's going out, and then eventually, over time, as more water is dropped out, it should go less and less distance, right? You can try it out. I'm not going to waste an entire water bottle on my floor. Now, the second part to that example that I want to talk about is how long it would take. Is there a way that I can change my time constant, right? And there's two ways I could do it. One, I could start off with less water. I could start off with less charge on here, or less capacitance. If I had a smaller water bottle, I wouldn't be able to hold as much charge, or there wouldn't be as much potential that there is for me to leave, right? So if I have less capacitance, I have less buildup of charge, and therefore it's going to take less time for me to deplete. Second part of it is my resistor. The resistor in the water bottle example is how big of a hole do I place at the bottom. If I have a pin-sized hole, that would be the same as a very, very large resistance, right? It's going to take a lot more time for all of the water to flow through a pin-sized hole, as opposed to if I were to take a drill bit and drill a big hole through the water bottle. And then if I were to do it, it would allow more electrons to flow through per second. And so that hole is going to be the same as my resistance value. Now let's observe what happens graphically. Initially, I've charged up my plates to a certain voltage, right? There's a certain difference in potential between the top plate and the bottom plate. And as I close the switch, as I allow the electrons to flow again, we're going to look at what happens with our voltage as time progresses. As I measure it at a new time, what's going to be my new voltage? So initially, with a high voltage difference, there's going to be a high push. There's going to be a large drive for the electrons to go from one side to the other. And if there's a high push, that means that there's going to be a large flow of electrons. Well, as that happens, there's going to be less electron difference on the plates, which means that there's now going to be less push. So initially, I'm going to get a large change in my voltage, but as time progresses, that change in my voltage decreases. So we should get a graph that looks similar to this. Now there's one main spot that I want to look at on this graph, and that's going to be what happens if I measured my time somewhere on this graph at a value of tau, or our time constant. What's going to happen? Well, if I put in the value of tau for my time, I should have negative tau over tau, and I get a value of -1. So if I have voltage multiplied by e to the -1, anything to the negative first power is 1 over that value, right? So it should look something like this. And this value of e, again, is just your calculator value of e. It's the inverse of natural log. So if I look at what happens as my new voltage at a value of some certain time, which we're going to use tau, is going to be my initial voltage over E, or about 37%. So suppose I charged up a capacitor with a 9-volt battery, right? Then the difference in my potential between one plate and the other should be 9 volts. Then, if I were to measure out my time constant, I charged my capacitor up, right? And I put it into a circuit where I have a capacitor and a resistor. and I measured at some time constant, I should have about 37% of what was initially there. So if I have 9 volts over E, I should get a value of about 3.3 volts. So as my time constant gets to a value of tau, I should have about 3.3 volts if I started off with 9 volts. Then again, let's suppose I went to 2 times my time constant, right? If I doubled this value, my change in voltage then would drop by about 37% of what it was initially, and 37% of 0.33 should be somewhere about 1.2. So we're talking about discharging a capacitor, but what about charging a capacitor? Suppose that I now have a circuit where I have something like a battery involved in the situation. All right? Looks like this. So it looks like this, where I have a positive voltage on one side of the battery, negative voltage on the other side of the battery, and my capacitor right now is discharged completely. Right? As I close my switch, well, the electrons are going to be allowed to flow, right? And I'm going to get a buildup of charge onto my plates. So my electrons are going to try and get away from the negative side of the battery as much as they can. So we're going to actually start to get a buildup of electrons on the bottom side, right? And we're going to get a buildup of positive charge on the other. As these electrons flow through, they try and put a big charge over here, and then it'll end up repelling them from the other side. So I'll be left with just positives, right? But how long is it going to take to do it? How is it going to do it, right? Well, initially, again, there's no difference, so it's going to be easy for the charge to flow. It's going to be easy for it to try and push into the capacitor, right? Because there's no difference in it. But as time progresses and I get a more and more negative charge built up onto my plate, it's harder for me to add more electrons into it. Kind of like if I start to put 50 people into the room and then I try and put 1 more person, 2 more people, 5 more people into here, it's going to be harder for me to find space for them, right? So that same thing happens. As time progresses, it's going to be harder for me to build up more charge. So we would end up getting something where my initial at time 0 is going to be easy. So there's going to be a large buildup of charge very quickly. And as time progresses, I end up getting close to the charge of my battery. But it doesn't quite get there. Again, because as time goes to infinity, as my time progresses, I will never reach my asymptote or the charge on my battery.